I'm Jonathan Turner from Radioactive Waste Management, and this is the session, in fact, I was going to say this is the session on plate tectonics and resources, but actually looking at the talks, it's the session on plate tectonics and oil and gas, and maybe that's something that we can talk about in the general discussion at the end. The first speaker is a keynote talk. It's Tony Doré, who has spent his, he tells me the last 25 years of his career at Statoil. Tony, you're most welcome.
Thank you. Okay, plate tectonics and the oil industry. That's a very big subject. So myself and my co-author Eric Lundin got the help of quite a lot of really good scientists here who provided some material that are going to go into this talk as well. Now, although all these people contributed material that we're using in the talk, they're in no way responsible for any crazy ideas that might be expressed in the talk. That's entirely down to me and Eric. Blame us for that. Now, some of you may realize that this conference is a sort of companion to one that happened last year. There was 50 years of the Wilson cycle, also held at the Geological Society. And I read somewhere recently that Dan doesn't particularly like the term Wilson cycle, pointing out that Wilson never actually said it was a cycle in the first place. And that's a pretty reasonable point. However, I'm here to tell you today there really is a Wilson cycle. I've been to Norway and I've come back with the evidence. And here it is. And you can see now really where some of these ideas came from. You know, it's all yeah. Okay, the petroleum industry and oil exploration. It's a big subject, so I hope you don't mind today if I skim lightly over some of the history, talk about the status of passive margin breakup, but then get on to a few things that are tickling myself and Eric right now. We're going to talk about a strike slip during breakup. How important is it? A little detour into the driving force, and I'm going to finish talking about my current interest, which is in cratonic basins. So, now, everybody's been starting with some reminiscences, and I suppose I should follow the tradition here. So, a memory of college. You remember the first day some people said that they were doing their undergraduate course right at the time that plate tectonics broke. Well, I was one of those people. And following another tradition, I rushed home last night and tried to find a picture of myself at the time, and there he is. Now, this guy here looks like he would rather be at an open-air festival and studying geology. But in fact, I did have to study geology, and as Nick mentioned earlier this morning, what we had to study were these things. You've seen this picture already. Back to geosynclines again, these mysterious megabasins that somehow got crumpled up into mountains. And I heard also this morning that Marshall Kay later became a mobilist. That was great. But it didn't prevent me having to study these basins, and it wasn't just myogeosynclines and eugeosynclines, it was all these as well. Orthogeosynclines, zoogogeosynclines, parageosynclines, exogeosynclines, taphrogeosynclines, and paraleogeosynclines. I've put zoogogeosynclines in red here because I'm playing a game as we go through this. It's spot the zoogogeosyncline. They're going to come in later. Yeah. Okay, so staying with the ego trip just for one little while longer. This is basically me. These are the last few decades of the 19th century, and I started as an undergraduate here, started as a postgraduate there, and joined the oil industry right then with Mike Ridd sitting in the front here as my boss. So this really was a cataclysmic time. I started out learning about geosynclines. My final year dissertation was about the opening of the North Atlantic. That's how radical things were. And so you know all of these advances. We've talked a lot about these now in the past few days, and I don't need to go through them. These were happening while I was an undergrad. But something else, particularly in the UK realm, was also happening that was really important, and that was this. We had the first commercial North Sea surveys. We drilled the first wells in the North Sea. We discovered the first oil in the North Sea. And the North Sea was important because it was a testing ground for the breakup models that led to plate tectonics. So this was very significant as well. These weren't the first offshore wells. That was a couple of decades earlier. But these were the first wells in the North Sea. Something else happened at this time as well that hasn't been mentioned so far that was equally mind-blowing to the geological community of the UK. The letter M here has come on, and M stands for Mokrus. Mokrus was a borehole that was drilled offshore Cardigan Bay, basically on a beach, and it found one of the thickest Jurassic sections in the British Isles, right offshore from the Paleozoic rocks of Snowdonia. And what that basically showed was that Cardigan Bay was there for a reason. It wasn't just where the sea happened to bite its way into the land. There was a whacking great Mesozoic basin there. And just led to what was a difference in a way of thinking. It doesn't seem like it now, but the water is actually there for a reason. And it wasn't very long before this principle was applied. A few years later, we saw maps like this. This is the well-known Peter Kent map from the Woodland volume of 1975, where we saw that the whole UK was fringed by basins of this type, fringed by sedimentary basins that we didn't previously know about. So the Caledonides of Scotland didn't just continue straight into the Caledonides of Norway. It was interrupted by this whopping great big rift going down the middle, the Viking Graben and the Central Graben, which contains 30 billion barrels of oil. And of course, that's important because, not just because of the onshore-offshore thing, but also, as I've said earlier, because this extensional basin system here became a sort of testing ground for the way continents break up. So, just stating with the history a little bit, this is a diagram that myself and Roy Gabrielson had fun with back in 1995. And we were trying to chart the history of tectonic models on the Norwegian shelf, but it could really be the history of tectonic models anywhere. And we did it by trying to think of tectonic models as life forms evolving. And so here we see the period I was talking about earlier, the critical period, which is also the time of the drilling of the first wells. So the rootstock here is plate tectonics, of course. But if anybody's in any doubt as to whether this actually affected the petroleum industry, just look at this chart here. Because the plate tectonic way of thinking basically spawned a whole lot of side branches. So we knew what was driving transpression and transtension. Regional paleotectonic models, Peter Ziegler and others started using the plate basis, the plate model, as a basis for some of their reconstructions. And these reconstructions were actually done by the petroleum industry. The petroleum industry was participating in this. But most importantly of all, probably, we started to understand a little bit more about the way continents broke up, the way rifting took place, and the mode of sedimentary basin formation. And the most influential paper, I think, in the petroleum industry was this one here, and this was done in 1978. So then this is some remarks on the formation of sedimentary basin. Why? Because basically that led to this branch here, which is essentially we started to have a testable model for how basins subsided and how they thermally evolved. And that, of course, went straight into maturation of source rocks and so on, which is so important to the petroleum industry. So highly influential branch. So just finishing off this little historical chart here, there's one other thing I've got to add, which is that while all this was going on, these next few decades here, there was an almost exponential increase in the ability to run seismic, such that we were starting out, when I started in the oil industry, 3D seismic was only being used for field development. Not too much later, 3D was being obtained on a regional basis, leading right through to the sort of 3D coverage we've now got of passive margins and the very deep seismic lines and so on. And of course, that was facilitated by an equally exponential increase in computer power, which actually continues into this day. So that very quickly takes us up to our present status, and I hope that leaves you in no doubt the petroleum industry and plate tectonics are joined at the hip, and this actually helps to explain how they are. Now, what I'm going to show here, when I give the signal, is an animation, and with some trepidation, since they've not been starting recently, but what this is, hopefully, is it's a version of G-plates, which Chris Scotty spoke so warmly about on the first day, but it's an adaptation of that by Statoil into a program called 4D plates, which georeferences the information the petroleum industry uses onto a plate tectonic base map, just to give you an illustration of how it's being used. So could you please start the illustration, the animation? And is it working? Yes, it is. So here, the most obvious thing, of course, we've got the solid geology on the plate tectonic map, and we're going to close this up. This is going to close up almost to the end of the Triassic. And the obvious thing about the solid geology, of course, is you can see how one conjugate margin relates to the other, and you can make predictions on how you might be exploring on those conjugate margins based on this. So this is going to close up, and it's going to go all the way up to 200 million years. And I love the way that we'll see that Chukotka snuggles back up against northern Canada there. I always like that bit. Not sure whether it's right. And then we're going to, as we now open again from 200 million years, we're going to put something else on this which is useful for the petroleum industry. So now we've got paleotopography and paleogeography on here, and now we're going to sort of open it back up to the present day. And it's pretty obvious how this must be useful to us. As we see our paleogeography and paleotopography evolves, we can start making predictions about reservoir distribution and so on. And all these little polygons you're seeing flashing on and off here are areas of development of source rock that have been mapped by the various projects within Statoil, so we can again see how they relate to their plate tectonic setting. And here we are sort of coming up to the present day, and yes, that will probably be the end of this particular animation. Okay, so could you please move on to the next slide? I think you'll have to advance it up there. Or shall I try it? Okay, okay, that works. Right, this is another animation. This time we're starting a little bit more zoomed in, showing some other uses of georeferenced data on a plate tectonic database. And this, of course, shows the magnetic stripes. This is total intensity magnetic field here. And again, we're looking at the northern hemisphere. So could you start this animation, please? And are we going? Yes, bingo. So here we've got the topography superimposed on the magnetic stripes. And now we're going to close along the flow lines of relative motion, while we've got paleotopography going. And all of these little lines here are the structural features we can see mapped along the northwest European shelf. So we can see how those structural features basically relate to the evolving plate tectonic situation. And now we're closing right back up, so Pangaea is now all in one place, scrunched together, and we're going to come out again. And as we come out, you can still see these sedimentary basins. And very soon, as we come back to where we were, we're going to do something different here. There'll be a little pause, and we're going to show what else we can do, because this is very important. A lot of what we're looking at are shelves and passive margins in the petroleum industry. That's where most of the discoveries have been over the last couple of decades. Now we can see deep seismic lines and refraction lines actually on the continental margin, and as we start moving the plates along these flow lines here, we can see how these deep seismic lines relate to their possible position as the plates move. And now we're going back out again, and we're drawing those lines out again. And now we've got them combined with Bouguer gravity, just for fun. And now I think the final part here is we pan out, and we can see all of these lines laid out. And this is present day. Oh no, we're going to close again. Okay. The tide keeps going in, the tide keeps going out. And we can see all these lines georeferenced to their position and their position where they should have been at the time. And I think we'll just see this moving on out now. And I'm going to say a little bit more about these lines later. In fact, probably in the next slide. Okay, this should be we'll just let this go to its end. Okay, I'm going to move on to the next slide now. So I mentioned these deep seismic lines, and I mentioned that passive margins, of course, have been a focus for the petroleum industry for quite a while now. And these lines here I'm going to show you provided by ION, these beautiful deep seismic lines. These are right at the interface between the petroleum geology and plate tectonics, because they enable us to see, well, for a start, we can see the moho. We can see the stages of breakup and speculate on exactly what they might be. As we go from necking right through to attenuation to seafloor spreading. This is an example from a magma pore margin, the East Indian margin, and you can equally see lines here, like this one here, the Namibian margin, which is a magma-rich margin replete with seaward dipping reflectors and so on. The bottom line is we can say a heck of a lot about passive margins now from beautiful lines like this. And we can go on and do things like this. This is a map produced by Statoil's Research and Technology Unit. But first of all, I want you to look at this. Using deep seismic lines and other data, we can start to sort of appreciate the different domains that exist, the different domains of stretching leading to breakup. Lots of people have got different names for these, and of course they'll vary between magma-rich margins and magma-poor margins and all the stages in between. But once you have defined domains like this, you can start to map them out across the conjugate margins. And this is part of the central South Atlantic. So on this one, you can see that what happens along strike is equally important. We can see that propagation from the south that we heard about on the first day here, but also a propagation down from the north, complicated situation in between, magmatic margins and so on. And why does the oil industry care about this? Well, quite simply because these domains have got different degrees of prospectivity. These domains will, some of them will be better for the preservation of source rock and certainly for the burial and maturation of source rock. So, passive margins, there are still lots of questions to ask about passive margins, still lots of questions to answer. What controls magma richness is one that I'm particularly interested in. Is it just a matter of turning the gas up, turning the temperature up, or is extension rate and lithospheric composition equally important or more important? Precise breakup geometries. We heard about convex upwards faults earlier on. There's still lots of debate about precisely how breakup happens. How SDRs formed. We've got an idea of how they're formed, but we don't necessarily know how deep they go or what they're resting on. And of course, where in all this mess we're going to put the continent-ocean transition for our ultimate reconstructions. But I would say, from the oil industry point of view, these questions are now second-order questions. They're not fundamental questions about plate tectonics. We can make maps like this, which help us to explore, which is pretty good. So I'm going to use the last few minutes now to talk about some things that are interesting myself and Eric about plate tectonics right now, based on our work that we've done. And I'm going to start by going back to Tuzo Wilson's original question. Remember this question? Did the Atlantic close and then reopen? Well, this is a map of the present-day Atlantic, which says these are the various ages of seafloor spreading up here. These fuzzy red lines here are the continental joins. And I think the answer from this would be, yeah, well, sort of, but not exactly. We know, for example, that large chunks of Laurentia were left here clinging onto Avalonia and Baltica, and it wasn't a precise breakup. And there are some areas here, like the Labrador Sea and the Baffin Bay, which don't seem to behave in a Wilson cycle way at all. These areas were just sliced through. Both the orogenic belts and the craton was sliced through by breakup. So why exactly is that? I have to skip over things fairly superficially today, but to cut a long story short, Eric and I think it's something to do with this. This is a map of the central this is a paleogeographic map provided by GTEC, very nice one for the Valanginian. And we think that the breakup is probably something to do with strike slip. And that strike slip would be to do with transforms linking the huge Tethyan Ocean to an outpost of the Tethyan Ocean at the time, which was the Central Atlantic. And you'll notice that these transforms here are remarkably similar to the small circles in the Central Atlantic, as Xavier Lepichon was talking about on the first day here. And it strikes me that some of these features here look very like the features he was describing in Paleotethys. Even more interestingly, we think the same thing might be true of the Northeast Atlantic itself, that strike slip may have actually taken place before breakup. And the reason we think that is because of a mystery that's been bugging people for a long while, which is why it's the entire pre-breakup basin chain left on the Greenland side up here and left on the Norway side down here. The rift was essentially bisected by breakup. We also, when we look at the Northeast Atlantic, we see blunt margins. The basement actually thickens towards the line of breakup in most profiles that we see here. And the actual pre-breakup beta in the Paleocene was very, very small. And of course, you wouldn't need a very big breakup if this was actually sheared through, if this was actually cut through by something. Then to add to that, the only place where you see significant Paleocene faulting prior to breakup, where the world really drops away, is in this feature here, the Hellgraben, which is very, very deep. But this is in what could well be a releasing bend in the Northeast Atlantic system. And the faults there, you can see, are trending, the normal faults are trending obliquely to the margin in pretty much the way you would expect if this was a pull-apart basin. Lastly, there's an inevitability here about the movement of Greenland. We can see that Greenland is, as Randell was saying yesterday, is moving northwards at this time. You've got opening of the Labrador Sea spreading here. At this particular time in the Paleocene, Greenland is moving northeastwards, and it seems to be running like along in a tramway here between the Ungava Fault and the Northeast Atlantic with dextral slip on the Northeast Atlantic, which is sort of inevitable from this movement. Then later on in the Eocene, the Northeast Atlantic starts opening and Greenland starts moving in this direction. So here we have compression in the West Spitsbergen fold belt, and here we have compression in the Eureka fold belt. So put all these things together, and the concept of a plate breaking by strike slip before it actually starts to separate. I won't go through all this evidence again, but we've amassed some evidence that we think that this happened, that the North Atlantic tore before it broke. And I'm not a rock mechanics guy, but I believe it's mechanically easier also to tear a plate than it is to pull it apart by tension. And so this idea could apply to many other margins. One last thing I want to talk about here in related to the same thing. What is driving Greenland? So we can see here that Greenland is moving relatively northwestwards, and it's decoupled by extension here, and it's decoupled by spreading here. And then later on in the Eocene, it's decoupled along here, along the Labrador Sea and along the Northeast Atlantic, and it's moving northwestwards, and it's causing significant compression to the north. We can argue about the degree of shortening. One thing that we're pretty sure of is that there's no subduction up here. Now, a while back, I heard somebody say that slab pull is the main driving force for plate tectonics. Well, this cannot be being pulled by slab pull, and it cannot be being pulled by slab rollback. So what is moving Greenland? You've either got to imagine 3 minutes, okay. You've either got to imagine that it's moving, that it's surfing northwards on a plume, or you've got to imagine that traction forces associated with this breakup are moving it. I put this out here in the hope that someone in the audience will say, there's nothing to worry about, Tony. The answer is very, very clear. Please tell me if you think it is. Okay, a long way from the petroleum industry. Last 3 minutes, I just want to talk about this, which is my current interest. The oil industry has been moving quietly onshore again in the last few years. And this is a map of the production in the lower 48. These black numbers here are historical production. The red ones are production from unconventionals. And you can see here that if you just look at the Williston Basin and the Permian Basin, that the production from unconventionals is expected to actually exceed that from the original production of the basin. And of course, that's a prediction, but it's pretty important. It's like finding several Prudhoe bays in the middle of Texas. So this is a significant change. And the oil industry is moving back onshore. And this is probably equally important to plate tectonics, because as these plates were scudding around the surface of the Earth, these basins here were forming, and these are cratonic basins. They cover a significant portion of the Earth's surface, and they contain a significant portion of the Earth's reserves in areas like Western Siberia and so on. And by the way, did you spot the Zugo geosyncline? You did, good. So Williston Basin is one example of those. It's an intercratonic sag, and this is a basin that's been going down from the Cambrian. Almost every geological period is represented, so it's accumulated sediments over the last 600 million years. What is making this basin subside? All of these basins are sort of round. They're all sort of very, very shallow. This is no vertical exaggeration, rather like those things Tony Watts showed. Okay, second to last slide, I believe. So this is a slide that Mike Daly allowed me to use, and this is on the formation of cratonic basins. This is one idea for how cratonic basins might form and shows how they're related to plate tectonics. So basically in the supercontinent cycle, the continents scrunch together, you get over-thickening of continental crust, and that continental crust gets hot in the middle, of course, through radioactive decay. If it gets exhumed rapidly enough, it starts to sink and you form a cratonic basin. And Dan has also published a paper on this with a McKenzie and Priestley paper. This is one way that cratonic basins could form. And the question is it the only explanation? This is it? Is it? Okay. Okay, fine. So, yeah. So here's a map of the United States with all of the old Proterozoic fold belts cutting across it here, and we've superimposed the cratonic basins. And you can see there more or less is a correspondence between the fold belts and the cratonic basins. But on the other hand, these fold belts are very old and will have exhumed and cooled well before these basins formed. So there's still some mysteries to explain here, and I think that's a mystery where the petroleum industry could join with academia to try to get to the bottom of this, because as I say, the petroleum industry is currently moving onshore. So I want to leave it there, and I want to leave you with the thought that if you don't like anything that you heard in here, you can always check it on your iPhone app here, thanks to at least one of the gentlemen in the audience today. Thank you very much.
Thank you, Tony. We have time for questions. Rob, there. Sorry, I don't know your name. There. Yeah. Just wait till you got the microphone. That'd be great. Thanks.
Thank you, Ian Sinclair. I found the strike slip idea in the Northeast Atlantic quite intriguing. It's sort of a two-part question. Are you comfortable with the age of it in the Paleocene, or is there any chance it's older, as in perhaps even the Aptian Albion? And are you comfortable, how tight is the data that says that it's dextral, and is there any chance that it's synstral across there?
We think it's dextral because, I mean, the logic is if Greenland is moving northwards and it's moving relatively northwards compared to Europe, it's kind of got to be dextral. But if you look at, there's two areas that we're looking at in particular, the Hellgraben and also the Faroes themselves, where you actually see kinematics that are consistent with dextral slip. And Faroes is the biggest releasing bend of all. Aptian Albion, I don't know. Back in the day, David Roberts said there was a lot of distributed strike slip along the rift during the Cretaceous. We certainly think in the latest Cretaceous. Aptian Albion I'm going to have to think about.
Dan, get the microphone down to Dan here.
Dan McKenzie, a recollection. When I was working on sedimentary basins, I was at MIT and I shared an office with Bert Bally. And Bert said, from Shale, and he said, please would I come down to Houston and give a talk to the shale geologists, but I needed to be aware that most people in the room did not believe in plate tectonics. This was 1978. And that situation really only lasted for another year, right? The paper that Tony talked about had really an instantaneous effect right across the oil industry. And after that, I didn't hear any noises about people not believing in plate tectonics, which was an enormous relief because it was really 10 years after I thought we were done. Right?
We've got time for one more quick question.
Wolf Jacobi from Mainz. I wondered, you did not mention the Iceland Plume, but I think you can't understand the opening of the north around Greenland without it.
Oh boy, I was hoping somebody wouldn't open that can of worms. I describe myself as a plume skeptic, but not a plume denier. Yes, I believe that there's a lot of things going on in the mantle, like Nikki does, and I believe there's an anomaly underneath Iceland. And I did mention, if you remember, that one idea is that Greenland could be surfing northwards like a giant surfboard on the Iceland Plume. I don't like that idea, but it's one thing that has been mentioned. There is a significant mantle anomaly under Iceland. The key is how long has it been there? Did it arise in the Paleocene, or has it come all the way from eastern Siberia in the Triassic, like some people think? I don't.
Thank you. Thanks, Tony. I realise I didn't catch everyone. There will be time for discussion at the end. So the next speaker is Christian Heine and co-workers, and Christian's from Shell.
I guess being the ultimate proof that Shell believes in plate tectonics now. Okay. Yes. So the morning, Tony was asking me, "You're going to show any animations in your presentation?" And I was like, "Yes." You know, and he was like, "Oh, they're going to be way cooler than mine." And I think this time it's the other way around. So that was pretty good to see. So I'm going to be talking about time. You know, the sort of, it's more like an outlook in terms of what we currently working on, taking, say, the time-animated 2D view of the world into a much more, say, data-rich environment in the exploration workflow. I have to bother you with this. You know, do not buy or sell any Shell shares based on what I say today. And let me acknowledge a few people. Also, one of them is in the audience, Loken, but mainly the Southeast Asia Regional Ventures team in KL, which I've been working with, and Dietmar Müller and the G-Plates team at UCIT, Caltech, and NGU, who kindly provided some slides. So I guess I'm not at the age yet to provide a large sort of look back on what has happened in terms of plate tectonic evolution in science. But one of the things I sort of grew up with as an undergrad in the mid-late 90s was the Seaglass Paleogeography of Europe. And this is a publication, internal publication entitled Hercynian Suturing of Laurussia and Gondwana, published in 1988. And it's interesting to see that, you know, some people seem to pop up quite significantly, and I guess Chris Cortese is one of them, as sort of representative of, you know, trying to build these data-rich paleogeographic models. And I think that's probably also a sign that by in that sort of time, people started believing in plate tectonics. So 79 and 81 was pretty soon after that paper. For those who don't know those Ziegler maps, just a few sort of slides to show, you know, this sort of 2D plus time view of the world. And these maps are actually very data rich. One can probably debate uncertainties and, you know, how much data actually went into this. But they illustrate, you know, the sort of time evolution of the positional systems as well as tectonic systems over time. And that becomes interesting in the current sort of environment where we are actually working a lot more quantitative. And again, this is probably not something unique to Shell. This is sort of the play-based exploration workflow where plate tectonics really sets at the base, right? So anything we do is sort of governed by the plate tectonic theory and provides a sort of framework and quantitative framework to actually work on. So we've sort of trying to move away from the qualitative work at basin scale to actually build data-rich quantitative paleo-earth models. And primarily using G-plates as an integration platform at specialist level, while ARC and PaleoGS is, of course, the sort of corporate vehicle to drive things. But G-plates has a few sort of really cutting-edge tools, such as plate topologies and deformation, you know, the ability to sort of connect to web feature servers and suck in data from, say, PaleoBioDB, which was mentioned in Chris's and I think Bruce Eglinton's talks in day one. But we can also connect to forward geodynamic models, right? So we can take the plate kinematics and connect that to forward modeling capabilities. And so essentially we're trying to harness the interoperability to link to basin models, for example, paleoclimate models, and to do some sort of spatial temporal data analysis across scales. And one example I want to show you is from recent work I've been involved with in Southeast Asia. And again, it's probably not quite at the academic, but more as a sort of pragmatic sort of industry level, these sorts of things sort of evolve. And it's sort of an attempt to take, you know, our knowledge, both internally and externally, to sort of update our view on how the Western Southeast Asian margin has evolved over time, and come up with a time-dependent structural framework in order to sort of provide the exploration teams with means to do some sort of source-to-sink analysis and ultimately risk or de-risk acreage. So one of the things I did was to actually take seismic tomography and map subducted oceanic lithosphere underneath Southeast Asia as a proxy to say something about the evolution of subduction zones over time. And that's quite an interesting exercise in an exploration company to take a seismic tomography model and build a 3D Petrel model out of that, because it's sort of suddenly you're not dealing with 10 seconds travel time but 1,000 kilometers depth. So what I've done is to map a few slabs in that area, and that's again not a sort of novel exercise that's been done many times before. You see all those citations on the left. But we can do something Johnny Wu and John Suppi actually coined as slab tectonics. So we can actually take those slabs, try to digitize them in 3D, use simple sort of structural geology restoration tools to restore them to surface, to say something about the actual outline of that slab prior to collision or hitting sort of subduction zone system. You might argue that some of these things are probably not done properly, in the sense that we are not taking care of spherical geometries, but then we are restricting ourselves to less than 600 kilometer depth. And there's also, of course, things like slab thickening and all these sort of, let's say, relatively detailed things which we cannot take care of in the time frame given working on these projects. So what we can also do, so trying to get a handle on the temporal evolution of subduction zones is one thing. The other thing is to actually start integrating plate deformation into these models in a sort of dynamic way. And this is done, in this case, for the Proto-Andaman Sea, where we are taking a sort of restored continental polygon, which is dynamic in shape and evolves over time. And you see here initial crustal thickness, which is being sort of stretched by the polygon boundaries moving in G-plates, ending up with a sort of certain distribution of stretching in that area. We can also then sort of take all that stuff and build sort of very sort of bare bones reconstructions, which also contain those famous glitches Chris Cortese was pointing out in his animations. And I'm just going to step through it to illustrate. One point is that we believe now that the West Burma block, in this case here, is not being actually pushed actively by India, by the leading edge of, or northeastern edge of Greater India, but rather being sort of slightly sucked northward or sort of following the Greater Indian Plate in a much more back arc sort of type fashion. The other thing, which I think is very exciting, is the ability in G-plates to utilize the Python programming language. And I think many people of you will know this. And I got a bit, I guess, excited with the size of the logos there. So we can actually do some really cool things. And pretty much, in this case, what I'm going to show you is to evaluate the distance of our point of interest over time to the nearest continental block as a simple, sort of very crude sort of proxy for continental proximity. So we're going to be looking at a piece of interest which is now was at 100 million years roughly situated down in the Kerguelen area in the southern Indian Ocean. And we are tracking the distance from that point of interest, which is yellow here, to the nearest continental polygon. And as we sort of move forward in time, you see that the Elan Bank microcontinent there is the sort of closest continental piece. As we move forward, India then becomes the closest continental block, roughly 700 kilometers of distance away. And as we sort of move northward, nothing really changes. The story stays relatively boring until we approach the Southeast Asian subduction zone system. And then we get a sort of flip between certain blocks, which you might take as proxy for sediment sourcing, sediment sourcing regions, right? And that sort of nicely ties into one of the previous talks about the Aleutian arc, that we get, a few hundred kilometers of turbidites, for example, fed into a basin. The other sort of interesting thing which we can take, sort of take that sort of quantitative framework, and can you actually play the movie, please? We can take, and this doesn't look as slick as Tony's presentation before, but we can take synthetic paleo-shoreline models, and there's the Smith one, I guess former BP, there's Jan Golonka's model, and we can combine that, can you play that again, please? We can combine that with the paleoceanographic age grids, in this case the old 2008 publication, and rifts, for example. And then we can start asking questions about the relationships between, the spatial-temporal relationships between depositional environments and tectonics, for example. And so this is actually, I think, a pretty groundbreaking activity by the Sydney group, published by Nathan Butterworth, and this is courtesy of Dietmar Müller, this slide, where they've used plate tectonic reconstructions in conjunction with time-encoded data from the Andean range to look at ore deposit formation over time using machine learning algorithms. And they found out that there are certain, let's say, tectonic conditions which favor the formation of porphyry copper-gold deposits, which are, you need relatively high or rapid convergence rates, a subduction obliquity of 15 degrees, subduction plate ages ranging between 25 to 70 million years, and a relatively, you need to be away from the trench quite some distances, so more than 2,000 kilometers. So I think, just as an outlook, this is pretty much where we are going, and I think big companies are usually very bad at keeping sort of track of data. One thing I think Shell has sort of a slight advantage in, although it looks a bit like Web 1.20, is a sort of corporate data store of basin models Shell has been working on. So this is sort of all the legacy basins and the ones we are currently working on in one place. And that sort of gives a nice advantage in the sense of looking at structured data and spatial temporal data analysis. So this is, I guess, one of the steps we're taking. So to sort of summarize these things, I think in general, plate tectonics is sort of very ingrained in the overall exploration workflow. But what happens is that we have tools like G-plates, for example, which allow us to really take a next step, building much more quantified, data-rich models like Bruce and also Chris have shown, and actually ask new questions. And most importantly, actually bridge the scales between plate and place scale. So for Southeast Asia, just a very quick summary, we can use this sort of Pi-G-plates interface to test proximity over time, to better constrain sediment sourcing. We think that the West Burma block is sort of trailing India as in a more sort of back-arc type fashion into its present-day position. And I think, as I said, we are stepping towards a much more sort of 3D plus time view of the subsurface by being able to integrate proprietary and external sort of data sources into a really quantified dynamic time frame. So that's, I think, where I want to stop. Thank you. More time?
Questions for Christian?
All clear.
I heard copper porphyries mentioned there, so we have dwelt onto resources other than oil and gas. So any questions for Christian? We've got time. Yeah.
I'm Jean-Christophe Robel-Davot from Halliburton. I've got a question about the machine learning animation that you showed. I guess to go back in time, with this example, you're kind of limited to where you have oceanic crust, right? You can't really go into deep time because you need the plate boundaries to go further, or how? Do you have a comment?
Yes. I mean, again, I was not involved directly in this work, but I mean, in general, yes, you need your oceanic crust or your synthetic oceanic crust, which you believe in, to be present, yes. And that sort of ties back to, I think Chris Scotese was showing that slide earlier on day one in terms of, the robustness of models back through time. So, yes.
Yeah, fine. Just one moment.
Mike Ridd. Rather a specific question perhaps about Southeast Asia, but I wonder if you subscribe to the view of Tony Barber and Mike Crow, who about 10 or 15 years ago postulated that West Burma was the northern extension of Western Sumatra, and now Western Sumatra has a fairly convincing Cartesian flora and fauna, which really required dextral slip from Eurasia to get outside those sort of Perigondwanan blocks before the Andaman Sea developed and separated West Sumatra from Western Burma. I wonder if you've any thoughts on that.
Let's say my sort of personal legacy would say that I don't believe into it. So I thought, don't you believe it? In the sense that it has sort of the Cartesian origin. So at some stage, I guess more than 10 years back, I actually worked on the sort of Argo-Abyssal Plain in Australia. You know, sort of looking at the magnetic lineations and implication this has for the evolution of the Eastern Neotethys. And I think there's quite some sort of belief that there's a ribbon terrain which sort of rifted across the Neotethys at that stage. How that sort of got sliced up and diced up in the subsequent convergence history, that's a sort of different matter. But I think it's still sort of hinges on the question, you know, what sort of assemblages we find in the Indo-Burman ranges, you know.
Thanks very much. Thanks, Christian. So the next speaker is Adilkhan Baibatsha, and I hope I pronounced that correctly, from the Kazakh National Research Technical University, and Adilkhan's going to speak on plume tectonics, among other things.
I am sorry for my not so good English. London, here, Almaty. Distance about 8,000 kilometers, but thanks to airlines, I am here. New data on the deep structure of the crust and upper mantle of continents form complex studies of the international system geotravels were collected. Some of them have been laid through the territory of Kazakhstan. On the basis, the models of the lithosphere to a depth of 100 kilometers in the Republic were established, which revealed non-uniform block structure of the upper mantle. Asthenosphere in the geosuture areas rise to the level of 18 kilometers, and asthenolates penetrate above the Moho in crust. According to current data, Kazakhstan is a continent. Kazakh by Karanovsky was existed independently starting since Neoproterozoic, before the complete formation of the supercontinent Pangaea II. Kazakh continent was developed without active and direct influence of the neighboring continents, but with the characteristic geodynamic and geochemical conditions. The isolation of Kazakh continent was promoted, the alleged split of the Rodinia megacontinent, and the shifting of the subcrystal part of the planet. Kazakhstan as a part or fragment of Rodinia. Assigned by the modern geophysical data, that is introduction of the plume and picked materials from the mantle and the asthenosphere into the lithosphere led to local rising and the formation of a fixed nucleus in the form of a ring structure. The nuclear ring structure diameters were approximately 3,000 kilometers. The formation of such a peculiar geological structure is associated with the action of the superplume in the Paleozoic and is clearly visible on the geological and tectonic maps of Kazakhstan and the similar maps of Eurasia. Fragment of map of Eurasia, Kazakhstan here, and three ring structures visible. If you look at the visible things, originally the correct shapes and size of rings were deformed later. Kazakhstan has east-south path is active margin, and north-west path is passive margin. At present, about 30 to 40 plumes, super plumes are known. They cover a surface area of a diameter of the order of several thousand kilometers. Some of them operate periodically, nobody's. Most of them are actively operating in the geological past, starting with the Archean and the Proterozoic, and the subsequent periods of the Paleozoic, Mesozoic, and the Cainozoic. Superplumes are known within all continents and associated with them as a formation of large ore deposits. The action is manifest in the form of active tectonic movements and large-scale volcanic eruptions. So conversion of the ring structures with the introduction of the plume, superplume in S, in the observed. The superplume, which was active in the Paleozoic, covered most of the territory of Kazakhstan, as well as the territories of neighbors countries, Uzbekistan, Kyrgyzstan. On the surface, the action of the plume manifests itself in the form of ring structures limited by active geosuture zones. Due to such features of geotectonics of the territories, the lack of linear geodynamics, which were depicted in the tectonic schemes of Kazakhstan at the end of the 20th century, served as a reason for abandoning the geochemical geocynical paradigm. As adoption of plate tectonics, which is well coordinated with geotectonics and the geodynamics of planetary scale structures, attempt was made to correlate the tectonic surface of Kazakhstan with its basic elements. However, the mechanical transfer of plate tectonics elements, even in planetary scale, did not find confirmation at practical geology, and introduced confusion in the tectonic and geodynamics of the territory of Kazakhstan. The sophistication of the application of the principles of plate tectonics is particularly well seen on maps where within the microcontinent of the Kazakh continents and the oceans have been identified, which are respectively only geological blocks and base and the strengths of the seas of neighboring Paleozoic oceans, for example, Paleoasiatic, Urals, and Tethys. All the paleogeographic reconstructions of the Paleozoic Kazakhstan is shown as an isolated and integral microcontinent island from Cambrian to at the end of Paleozoic. For example, it is impossible to imagine the extent of oceanic vision, such as limited size of the microcontinent nuclear. Kazakhstan only here, without intra-oceans and intra-continents. The internet plus of the planet caused the vertical movements of nuclear. This caused the formation of concentric ring structures. The foundation of the ring structure served the atmospheric materials and the lower mantle to sink in the form of relatively ring core in the lithosphere. So the Kazakh continent was developed under the direct influence of this foundation. Rather, ring structure under the pressure of the plume was subjected to brittle fracture in some places with the formation of random faults, cracks, and mosaic structures. The continent has accomplished mostly horizontal rotational and vertical oscillatory motion. During the rotation of the continent around its axis there was a strong pressure and friction between the rings. Geosuture and the weared out mantle zones of compression or stretching with widths from tens to 100 kilometers or more. Through these weakened zones, in the lithosphere, active molten mantle materials were penetrated, which sometimes reach the Earth's surface. Schematic structure of the Kazakh continent. Three ring structures, inner diameter about 600 to 800 kilometers, second and the middle ring structure, and the external third ring structure. Each ring structure limits geosuture zones. 3 minutes. 118 seconds. Okay. The stage of formation of ring structures. First stage, second stage, and the third stage, and the 3 ring structures respectively. On this slide shows that large deposits or deposits are located only the geosuture zones. First, second, and the third ring structures, and respectively geosuture zones. Chromite, platinum, gold, and well-known copper deposit, Kazakhstan, and etc. Oil and gas basins. Kazakhstan is surely among the elite of the world's hydrocarbon carbonates. Kazakhstan has a huge reserves of oil and gas fields. The most significant increase of the recoverable reserves and production of hydrocarbon raw materials can be expected due to Caspian Sea. And such studies will identify that the main centers of generation are in the process of generation of liquid or gaseous hydrocarbons to identify which ones are most similar existing fields, which makes it possible to solve the issue of determining the highest concentration areas and type of the oil gas deposit in other less studied basins here. Conclusion. Ring structures of Kazakhstan are also reflected in the physical fields, particularly in the gravitational field. The faults separating the crust into a number of the Kazakhstan megablocks and blocks. The most significant of them, according to geophysical data, cut the crust for all the thickness and penetrate into the upper mantle. Such structures are formed in the early stages of the development of the territory and acquired a modern appearance in the form of Ural-Mongolian belt in the Mesozoic. And this presented option of map of Kazakhstan may serve as a scientific base to predict perspective mineral deposits and oil gas deposits to find new source of them. Thank you for your attention. Thank you for your attention, if you understand me.
We do. We've got time for questions. Yeah, Mike. Rob.
Mike Reid. Another reminiscence with a little question at the end of it. After my career with BP, I was looking after a small oil company called Croft, and we got an involvement in Burma, where we drilled a well, and it was dry. So we were looking around for somewhere else to explore internationally, and we settled on Kazakhstan. So I flew off to Almaty, and I met with the government officials. Yes, they said, we can give you some acreage. And they gave us some acreage, and we started studying it on the maps. And it turned out that right in the middle of our block was the Baikonur Cosmodrome. So we thought this was probably not a good idea. We might have a few operational difficulties there. So we went back to the government, and they offered us a block close to the Turkey, the southern Turkey Basin, and where there's the very large Kumkol oil field. But the interesting thing to us was that with our North Sea experience behind us, we saw something almost like an onshore version of the North Sea. You had a north-south graben, I think containing probably Jurassic rocks, and then a period in which rift deformation ceased, and above that you had this great depressed, sagging blanket of younger rocks, Cretaceous, I suppose, Cretaceous and Cenozoic. Could you comment on that apparent similarity between the North Sea and the Turgay Basin?
North Sea and Turgay Basin. Maybe, who knows, maybe. Thank you.
Nothing wrong in that.
Thank you for your comment.
Thank you very much. The next speaker is Frank Ettensohn from the University of Kentucky. Frank.
Good afternoon. I'm Frank. I'm from another UK, University of Kentucky. And in case you don't know too much about Kentucky, we're famous for fast horses, bourbon whiskey, and of course, Kentucky Fried Chicken. Like many of you, I was brought up on geosyncline theory, and it wasn't until maybe the early 70s when I was in grad school, we had a rather dynamic Welshman who had been transplanted from the UK into Illinois named Dennis Wood. Some of you may have known Dennis, but Dennis is the person from whom I first experienced plate tectonics. But anyway, we've heard many different approaches to plate tectonics. I'd like to suggest yet another one is black shales. And as you can see, not only are there geologic aspects of this, there are also economic and political aspects. And I worked for a year in 2014 for the State Department. And I was sent around the world trying to counter the effects of Gazprom and some of the anti-fracking propaganda that was being put out by Gazprom. This rather garish and busy slide kind of reflects what's going on today in some of the U.S. oil and gas fields. It's like the Wild West all over again. Also in China, I've been in China, same kind of thing going on. Everyone's trying to produce gas cheaper than the next guy to counter the effects of OPEC. When I was at the State Department, these documents came out, and this was the U.S. government's attempt to try to get all nations on board fracking and gas shales. This was a way to give everybody energy independence. They produced this map of all these gas shale basins, and they issued estimates of this sort about the relative abundance of gas in these various basins by country by country. Some of these we learned were great over-exaggerations. Some of them were under-exaggerations. China was supposed to have more than just about anybody else, and of course that hasn't come out. Today what you see is mostly we're dealing with North America, United States, and Canada. China has very little right now, and in my estimation probably will not have a heck of a lot in the future. But the U.S. share continues to grow. Now, these are the U.S. shale basins. We've seen some of these before. There are greater than 30 of these different shale basins, and of course these were all touted as important during the shale revolution. And what we've come to realize, it really isn't so much an revolution as it is really an evolution. And it's a phenomenon related to the geology of North America. And there's also developmental and promotional aspects to this that I'll talk about a little bit later on if I make it to the end. So one of the questions we asked continually in the State Department was, why are there so many basins across North America, and can the North American experience be translated or moved to other countries so these other countries can have energy independence? So we looked at many of the geologic factors. Several geologic factors. The North American continental Laurentia has been a large, stable area for most of its history. This is a slide that shows the breakout of Laurentia from a bunch of other smaller continents. And throughout its history, it's been a very large continent and continues to be. And in these very large continents, we can get a large number of basins developed. Throughout most of its history, Laurentia was also a tropical or subtropical continent, very favorable for the production of organic matter. So a lot of organic matter. These are some Devonian shale basins shown up here in this particular rendition. So these are North American shale basins, mainly Devonian, Mississippian shale basins, but what you can see is we have a series of deformational belts or orogenic belts along the margin. Appalachian orogenic belt. Here are 5 different orogenies present during that time. A Ouachita belt, another orogeny, the Cordilleran belt all along here. The deformation is pretty much limited to the margins, but the continental interior is relatively undeformed and lithologically and structurally uniform, which means it's much easier to do fracking and horizontal drilling when you don't have to worry about all these structures. Now, most of these basins can be characterized as either foreland, compressional foreland basins, or extensional rift basins. I'm going to emphasize these things, but this is a little model showing we have some subaqueous loading here. This is when we think a lot of the black shales developed. Rapid subsidence, not much in the way of clastic input. Later on, when we have subaerial loading, we get a bunch of clastics coming into the basin that serve to protect those organic shales and actually serve as reservoirs for some of the more conventional drilling. This is the extensional rift basin model. I'm not going to talk too much about that, but they're also important in what we see in North America. So this is just another outline of the basins in here. The red basins are largely rift or rift margin basins, things like the Haynesville, the Tuscaloosa, the Burgos. These are all extensional rift related basins that formed during the breakup of Pangea. Out here we have some deformed forearc basins, the Monterey Shale out in California, Jurassic in age. But again, I'm really more interested in here in the black basins. These are foreland basins. Another set of foreland basins in here. Another set of foreland basins in here. And then a whole series of yoke basins that have been intracontinental or intracrotonic basins in here. And I want to talk also a little bit about the relation to these foreland basins. And today, a lot of we have major black shales here in the Appalachian Foreland Basin, again in the Permian Basin down in here, also in the Cretaceous black shales up here, and also yoke basins. So talking just a little bit about these foreland basins, how do we create these basin repositories for this shale? And all along, I don't think it's anything, there's plenty of organic matter, but it's how we preserve that organic matter, and we need basins for that, and the answer, I think, are tectonics. And I think that many of these black shales are inherent in the formation of foreland basins. And so what I've gone about and done is actually mapped the distribution of black shales in time in the foreland basins. So these happen, this is an Acadian or late Devonian, well, actually lower Devonian to late Devonian Mississippian time, mapping these basins, and what you see, this is the Marcellus, lower Devonian, two basins that join to form the Marcellus. And then interestingly, in the latest Devonian, we have a whole series of cyclic black shale basins, but interestingly, these basins migrate. They migrate in time to the southwest, as you see here. And so they not only migrate to the southwest, but they also migrate cratonward. What we're finding is that these basins are they're part of unconformity-bound sequences, and we relate these to tectophases, or phases of an orogeny. And it turns out that many of these orogeny phases are related to individual convergence with promontories on the margin of the Laurentian or Laurentian continent when they formed. All right, Ordovician. This is the typical tectophase sequence, black shales, flysch-like, a transitional, molasse-like. We see these kinds of cycles throughout our black shale basins. We have 13 of these cycles in the Appalachian Basin. This is Ordovician, and here, Taconian. And when we map these basins, the little black one here, Sevier, this is the Utica-Martinsburg, this is a lower Silurian basin. The orogenies, the tectonic, starts out here south and migrates to the north. The basins do the same thing. The basins actively follow or track the progress of orogeny. And here we have a cross-section AD. Here is the middle Ordovician tectophase down here. Again, the sequence, unconformity, transgressive carbonates, black shales, flysch-like, molasse-like, unconformity. Here's the next one. So the basins are migrating with the orogeny. And even here you can see the black shales getting younger in time as it moves northeastward. So there comes a time also when we're able, I think, to relate basins to actually subduction vergence. Early on, we have an eastward verging subduction. We open these basins up. These are old Iapetan rift basins that get opened up. This little bit of business right in here is the Flat Creek deposited in there. Then subduction vergence changes, and it becomes westward. Now we have a compressional cratonic regime, and what we see is our black shales start to migrate out of the Appalachian Basin and actually yoke with the Michigan Basin. So our shales are actually moving in time, and although I can't prove the direct correlation, these are metamorphic and igneous ages, these are biostratigraphic ages, they do overlap, and there's some suggestion here that we can relate these black shales to changes in subduction vergence. Another important thing about North American black shales is they're stacked. We have a lot of stacked basins. This is the Appalachian Basin, Taconian, Salinic, Acadian, Neo-Acadian. These are all basins that have black shales that are potential oil and gas shales. We're also starting to get black shales now in the Iapetan rift basins, and here companies now actually starting to prospect some of those in Kentucky. So we have these stacked horizons, the Utica, the Marcellus, other upper Devonian shales, again, making it relatively easy to drill many multiple horizons. This is the Permian Basin. We have 13 stacked plays in the Permian Basin. Yoke basins. It turns out when we actually have these long compressional waves that unite foreland and intercratonic basins, and we get basin yoking. These are Devonian Basin yokings where you get black shales moving from the Appalachian here, from the Antler Foreland Belt into the Williston, from peripheral foreland basins into intercratonic basins. This is the Ordovician situation again, where shales migrate right into into an intercratonic basin. So just to summarize, our geology here, these are the three things we think are important in understanding shales in North America. A lot is geology. We understand a lot of that. We've worked with this since 1975 in the Arab oil embargo. Technology came along with horizontal drilling in the 2000s, and right now it's a matter of economics. How can we do it more cheaply? And a lot of things about ownership of land, private ownership of land helps a lot because everyone wants to become rich. And so this has been a really important aspect in our economy. Thank you very much.
We've got time for a quick question. Yeah, Tony. Frank, if you come up here and answer the question, then everyone can hear you.
Yeah, really nice presentation, thank you. I agree with most of what you say about the technology and certainly the commercial terms and conditions that actually help this along. I love what you said about yoked basins. It's the sort of way that we're also thinking in our work. Wasn't totally convinced, though, about the geological arguments. I know that the international unconventional production is probably not going to match up to the initial expectations. But surely, bottom line is, there are other forelands around the world, there are other stacked plays, and there are other black shales which are frackable. So even if the conditions are ideal in the US, surely they are going to occur in other places in the world.
Not to the same extent. A lot of the basins in the other places are relatively small compared to those in the US. European basins are relatively small. The Chinese basins are relatively small. And what we're seeing in many of these basins is that, at least in the US government, when they made these initial estimates, they didn't take into account tectonics. They didn't take into account the possibility of overmaturity in shales and things of this sort. And that's what we're seeing now in China, for example. They have a relatively big Sichuan basin, but the shales there have been intensely thrust and are largely overmature now, with a few exceptions.
There's one country you didn't mention, though, and you're probably not allowed to mention it, but I will. All the way down the Urals, of course, there's a series of fallen basins.
The Bazhanov Basin, probably one of the biggest shale basins present. But right now, I think the Russians have so much conventional oil and gas that they really don't care. And Exxon was brought in there basically, and of course with the embargoes and things that are going on with the Ukraine situation, a lot of that investigation now has halted.
Okay, we'll leave it there. We will have time for questions as part of the wider discussion at the end. Thank you very much, Frank. And
we're on the third day of a brilliant meeting, and I thought, given the industry talks, and particularly Professor Eddinson's talk about shale basins, that it'd be appropriate to make the linkage between this very strong evidence from a number of people that the interiors of continents are critically stressed, and that deformation does not just occur at the boundaries. And so the ways that we approach exploration and the ways that we examine these areas, not necessarily with the reconstructions of the boundaries themselves, but the present-day deformation and the mantle structure. And Nikki's talked about this, Gerald Roberts, many people here at the meeting have. And what I'm wondering is whether the new exploration strategy for interior basins is to have a risk assessment and evaluation of active deformation that won't necessarily have the same patterns or structural orientations of the exploration targets, but should be an evaluation. I don't think anybody wants repeats of Oklahoma. And we all want to see our students employed, so yeah. But I mean, is that a target? Is that something that it has been discussed or within industry?
Well, just vis-a-vis the comment on critically stressed plate interiors, I mean, my earthquake app on my phone is always dominated by poppings off from Oklahoma and wastewater injection in intraplate United States, so you're right there. But any general comments on that? Yeah, Tony.
Yeah, Tony Doré. Yeah, I think it's already being done, and I think present-day stress is being regarded as important by the companies in terms of exploiting present-day stress systems in when getting unconventional resources. So I think that's probably true. The other thing that I've learned a lot about recently is microseismic, which is what you've just been talking about now, how you can actually use the present-day response of fracture systems in the subsurface to fracking and horizontal wells to actually determine the anisotropy in the subsurface. So I think there is quite a lot of work there, and I think it's a fertile ground.
I mean, to give an example, Cindy, of you know, how what you've said can be put into practice. I mean, my time with BG working in the coalbed methane play in the Surat Basin, Queensland, one of the keys to targeting sweet spots early on there was to understand the relationship between the coal cleats, these are Jurassic coals, and the in situ stress field. In other words, to target places where the coal cleats were favourably aligned with respect to the maximum horizontal compressive stress. Any other questions? Yeah, here, right at the front row.
Question for Frank.
Just wait till you got the microphone and say your name, please.
It's John Hancock from Oslo. It's a question for Frank about his internal intracrotonic sag basins, as we'd say in Exxon, that to have 5, 10 or more productive or prospective shales in one basin seems quite strange given normal geothermal gradients, which you didn't mention. I wonder if you could comment on the geothermal gradients and the paleogeothermal gradients, perhaps.
I'm really sorry. I really don't know much about that. I'm a sedimentologist. It's my only excuse. But what we can say, some of these, the cyclicity, for example, the Permian Basin, that is related to Gondwana glaciation. And we have many cycles of black shales and intervening clastic units in the Permian Basin, and that's clearly related to Gondwana glaciation and the cyclicity of glaciation. So that might help explain the Permian Basin. The other thing is the other cyclicity that we see in the Devonian, for example. We think that is related to big thrust complexes periodically coming, and that's related to oblique convergence of a terrain, Carolina terrain, with the margin of Laurentia or Laurussia, whatever you call it at that time. But I don't know anything more.
Dixon Cunningham.
Just a quick question, scanning the globe, thinking of other areas that may be prospective for oil and gas shale prospectivity, potential areas of exploration. I immediately thought of the eastern flank of the Andes, 5,000 kilometer long foredeep with a few gaps from Ecuador to southernmost Argentina. And how would that be different than the Cordilleran foredeeps in North America?
Mike Daly.
Well, it's a question. I mean, the quick answer to that question is that exploration of that type is happening there right now. The Neuquén Basin of Argentina is an obvious example.
Yeah. Mike.
I mean, that's the point I was going to make. There's a thing called the Vaca Muerta, which for the Spanish speakers amongst you will know as the dead cow shale, and that's that on that diagram that Frank showed had, I think Argentina was the third largest resource holder of this stuff, and it clearly happens there. But the thing that no one's mentioned so far in this is the Middle East. The Middle East is going to be a major shale play, and you know it's a lot of this thing about exporting it, Frank, is all about people needing to. And the biggest shale in Russia is actually on the east side of the Urals, not the west, and that's a Devonian one akin to the American one. So you know there is a lot of this out there, but the uniqueness of the love of technology, the love of investment, and the love of risk taking, and a reasonable authority is why it's so special in the US.
Okay, thanks, Mike. We're going to squeeze in 2 quick more questions, just slightly eat into lunchtime, but it's a good discussion. So I don't know your name, sir.
Bruce Iglington, Saskatchewan. In part a comment, but also a general question to a number of the speakers that we've had today. We seem to be focusing primarily on transcrustal features rather than translithospheric. And yet, looking at some of the longer term stuff, I suspect that some of the major translithospheric structures could have a very important role in localizing which blocks are actually moving. Maybe someone would be prepared to comment on the extent to which that might actually influence some of the discussions we've been having.
So a quick response to that, or is that food for thought? Otherwise, we'll go on to the chap sitting next to Nikki. Can you say your name?
Yeah, Dave Latin, not belonging to anywhere in particular of myself at the moment. Comment following on from Mike, though, is, it occurs to me with the shale argument, it's really all about the surface, and not the geology, actually. So it's about the economics, huge activation energy to get it really going anywhere else other than the States, where there's a perfect storm of conditions on the surface to do with land ownership, the number and availability of people and resources, regulations, and all of the things you need to exploit it that are very difficult to get in place anywhere else on any kind of time scale that will make sense, other than possibly Argentina, but it's slow going there.
Okay, so I'm going to take chairman's prerogative and ask a question that's rather unfair, really, but it's a question of Dan, who wasn't actually a speaker in this session. And so Tony rightly highlighted the impact of the 1978 paper on the petroleum industry, and I just wondered if there's any anecdotal background on how that evolved into the paper with Andrew McKenzie that essentially applied that theory to the maturation of organic shales. And maybe the answer is no.
The paper, Dan McKenzie, the paper that I did with Andrew McKenzie had a quite strange background, which was its original purpose was to use our knowledge of the physical chemistry of the reactions which occur in source rocks to test the sedimentary basin ideas. But we very quickly found that the physical chemists and the organic chemists had nothing to do with each other. So we knew nothing at all about the activation energy and frequency factor which governed that reaction. So we thought, all right, we'll do it backwards. We've got a good model. Let's actually calculate the activation energy and frequency factor from the geology, which is what we did. We then submitted the paper to AAPG, who sent it out to review, and the reviewer said, we can't understand any of all this, you should not publish it. So we then submitted it actually to the Geological Society. And one of my friends at that time, he was an editor. He was a paleontologist, and so he submitted it. And on the way down to submit it, he read it in the train. And they sent it out to review and got the same response. But he was a paleontologist and read it, and he said, it's perfectly clear, I understand it. So I'm the editor of Geological Magazine, and I'm going to publish it. So that we thought was the end of it. And so he published it. And then, to my absolute astonishment, and it's the only time it's ever happened to me, it won the award for the best paper in organic geochemistry published that year. So, with some delight, I sent this letter to the various editors who rejected it. It was the only time anyone's ever given me an award for writing a paper. It couldn't have been a better one.
There was a good reason for them not to allow you publication.
Thank you so much for that. Minutes. Can I lastly thank all the speakers who have contributed to this wonderful session with the round of applause that's the usual way. Thank you.